Hi guys. Okay, so let's look at chapter 10 on reaction rates and equilibrium, and we will be doing, this is a small chapter, so we are going to be doing the homework questions in this video lecture. We will do 13. Now 17, 18, 19 and 20 are similar, but I will do two, 17 and 19. Okay, and then 23, and then 25 and 27 are similar, so I will just do 27. Okay, and then similarly 29 and 31 are similar, I will only do 31 or 29, one of them, I don't remember now. So one of them. Okay, so anyway, so let's do this thing. And so it's going to be a short video and we can finish this quickly. So here, the first question is write the equilibrium constant expression. So you know that this side are the products, and in general that is favored. Okay, and the back side are the reactants. These are the reactants in a forward reaction. Okay, so now the equilibrium expression is K EQ or K constant is equal to the concentration of all the products, right? If whatever the products are, raised to the power their number of moles over the concentration of the reactants. Okay, concentration of the reactants raised to their power of number of moles. Okay, so here you just have to write down Kc is equal to the concentration of carbon disulfide, and for the concentration, so concentrations are the amounts. Okay, this concentration is written as square bracket. Concentration is always in square bracket, and that is the amount, and that amount can also, this is expressed as generally, molarity. Okay, so here, anyway, so here we have, I'm going to need space. So here we have the concentration of CS2 times the concentration of oxygen raised to the power 4. CS2 only has one coefficient in front, so we don't write that. But for oxygen, we will write it raised to the power 4 over the concentration of the reactants, which is sulfur trioxide, SO3, and this is raised to the power 2. Okay, times the concentration of CO2 raised to the power just 1. So for 1, we don't write. So that's the first question. So you write down the concentration. So here, it's very important that you understand that the raised to the power factors, these things, balanced equation. So that's important piece. Okay, and then the reactants is in the denominator, products on the numerator. So that's our expression. Next is they're saying calculate the value of Kc. So here the equation is given to you that N2O4 is giving you 2 moles of NO2. So what is the value of Kc? So Kc, write down the expression first of all. Kc is the concentration of nitrogen dioxide, which is the product, raised to the power 2 over the concentration of M2O4, right? And then just 1. So let's just plug in the numbers. Kc is equal to NO2. NO2 is 0.21, brackets closed, raised to the power 2, okay, over the concentration of N2O4, which is 0.030, and that's closed, right? And that's the concentration of the N2O4, and the rest is just math. So math is 0.21 times 0.21, if you understand the squares. And so that is divided by 0.030, and that should give you the answer. So here we have 0.21 times 0.21, divide that by 0.030, and you get 1.47. So Kc value here is 1.47. Remember that when Kc is equal to 1, which means the reaction is at equilibrium, which means the concentration of the products and the concentration of the reactants come out to be the same. But when Kc is more than 1, that means the concentration of the products is more than the concentration of the reactants. And when Kc value is less than 1, that means the concentration of the products is less than the concentration of the reactants. So this is like the very basic thing. If they're asking you what is the direction is it is moving forward direction. So it is at equilibrium, but it's forward is more like it's moving more towards the right side, moving towards the right side, forward side. Okay. All right. So that's one piece. Next is, so we got this. This was the problem number 17. And let's just check the answer. 17 is 1.5. So this is equal to, they have rounded it up, 1.5. Okay, so that's correct. Okay, and then the next is this one is also correct. All right, next is here, calculate the value of Kc. So the same problem, same way, just a little bit more complex. So Kc is equal to, here in this reaction, we have the CH4, the concentration of CH4, okay, times the concentration of water. Next is the concentration of CO, which is the reactant, and H2 raised to the power 3. So just plug in the numbers, and you have here CH4. CH4 is 1.8 molar times the water is 2 points. So just put it like that. So times 2.0 molar, that's the water. Okay, over the CO is 0.51 m. Okay, times that of hydrogen is 0.30. Now that is raised to the power 3. Okay, so the rest is just math. So raised to the power 3 means 0.30. Raised to the power 3 means 3 times, right? So 0.30 times 0.30 times 0.30. Okay, so that's it. All right, let's do this. 1.8 times 2, and that gives you 3.6. 3.6 over, next is 0.51 times 0.30, wait a minute, 0.30 times 0.30 times 0.30, and that is equal to 0.027. Okay, so times 0.51, and that is 0.013. Okay, so 3.6 divided by 0.013, and that gives you 276.92. That looks like a lot. 1 second. Yeah, so 276. 276.92. So this comes out to be actually 277, right? And that's the value of Kc. Now that's a lot. That means that like the reaction is moving in the forward direction. It's positive. It's a big number, and there is more concentration of the reactants, more concentration of the products. So yeah, and it makes sense also, you know. Okay, next is indicate whether the reaction will have more products or the reactants. So here they are asking you to look at the Kc value and make sense of it. Now Kc value, here we are not given the concentrations, but what they are trying to see is like, do you understand how to interpret the Kc value? Okay, so if the equilibrium constant, that's a huge number, so it's a positive number, right? So this is a positive number, and it's a huge positive number greater than 1. Therefore, Kc is going to be moving in the forward direction. And forward direction means that the concentration of the products is more than the concentration of the reactants. So this is the language. Okay, this is how we speak. All right, next is this number. Again, for this reaction, we are given the value of Kc, but negative exponent means that this is a negative number, means a smaller number. Negative numbers less than 1. Therefore, the Kc value is like the Kc is indicating that, you know, that the reaction is moving backwards. And when the reaction is moving backwards, that means that the concentration of the products is less than the concentration of the reactants. Okay, so this whole thing has been expressed in this way. That's the language for this particular, you know, like concepts. Okay, next is what they're saying, find the concentration of NOBr when you are given the concentration of the two products, that is the nitric oxide and bromine, right? And the value of Kc is given. So same story, you're going to write down Kc is equal to, here, the concentration of NO raised to the power 2 times the concentration of Br2. Okay, and this whole thing, concentration of NOBr raised to the power 2. Okay, so this is given to you. Right now, first, let us set it up first here. So the concentration of, so how would you do this problem? Here, NOBr, let's keep it squared. Okay, squared is equal to the concentration of NO, all right, square times Br2. And then here you have the value of Kc. All right, so let's do these problems first. So NO is 2.0, right? Raised to the power 2 times Br2 is 1.0, and that whole thing, and then Kc value is 2.0. So let's solve for this first, and this is giving you the NOBr raised to the power 2. Okay, so let's do this. 2 times 2 is 4 times 1, and then divide that by 2. So this is basically 2. Okay, 2. So here we have, so we have 2 and 1 second, the opposite. So N square, 1.4. Okay, to solve this NOBr when it is raised to the power 2, but we will have to remove that square. So that means under root 2, and under root 2 is 1.414. Okay, so you know, you solve it like anything that is square on one side of the equation, on the other side of the equation, it's under root. Okay, so I'm sure you know this from your math, but that's the answer, and that's the correct answer. Okay, all right, so I checked it, this is correct. So that is the value, this is the concentration. So for the concentration, you are going to write down the M. Okay, and because, you know, it's only 2 places after the decimal, sorry, so it's only 2 significant figures. So 1.4 is fine, M. That's the correct answer. Okay, now comes this question number 31. Now 31, I'm doing 31 in which I've taken the 3 moles of oxygen reacting with, like, are heated up to give you ozone. So this is a reaction that occurs up in the upper regions of the, you know, atmosphere, where we have like thunder and lightning. So that heat is coming from the thunder and lightning. So this problem is a Le Chatelier's principle. Okay, problem. So here we have, in this case, what happens. So remember, in Le Chatelier's principle, it is always if whatever change you apply on one side of the equation, you see the effect on the other side of the equation. So the whole thing is that you apply stress. The change is the stress you apply on one side, so the reaction is going to move in the opposite direction. So for example, here, if you're adding more oxygen, oxygen is the reactant. So you apply the change on the reactant side, so the reaction is going to move forward. So when the reaction is moving forward, so here, the reaction will move forward. So let me write this down here. The reaction moves forward, in the forward direction. And when it's in the forward direction, what does that mean? That the concentration of the products is going to be more than the concentration of the reactants. Even though oxygen is the reactant, right? You should assume that, oh, we added more of it. No, but the response is, it's the whole purpose is to bring that change. So we want more of the disrupt the equilibrium so that we can have more of the products. So that's what happens. Next is on the opposite end. Let's say the reaction is not going anywhere and you have a large excess of ozone from your side also, you add it. So you applied the change on the back side, on the product side. So here the reaction will move backward. And in this case, the concentration of the reactants is going to be more than the concentration of the products. Okay, now what happens when you apply a change? In other words, to the heat, temperature. Heat is also a product. So remember, is also a part of a reactant. So this is also, heat is also a reactant. So temperature means, increase in temperature means increase the heat, means increase that reactant. Okay, so in that case, what's happening now? So in this case, the reaction will move forward. Okay, because to wherever the change is applied, the response is in the opposite direction. So we see the reaction moving forward. And in this case, the products will be more than the reactants. So it kind of makes sense. The more thunder and lightning, the more ozone is produced. Simple, right? Now, volume. Now, that's a tricky part with volume. Now, rule regarding the volume is that it doesn't matter which side the rule follows the moles. So here, that the reaction moves in the direction wherever there are, like if you increase the volume, when the volume increases, the reaction moves wherever side that there are more moles. If you decrease the volume, the reaction is going to move in whatever side there are less moles. Okay, so that's the rule. So here we see, in this case, we increased the volume. Okay, so if you increase, the volume increased. So when the volume increased, you see that the oxygen has 3 moles, right? But ozone has only 2 moles. So there are more moles this side. Let me put this here. More moles on the reactant side and less moles on the product side. So if you apply, if the volume is increased, that means the reaction will move. Reaction moves. Let's put this here. Let's do this here. So the reaction moves more moles, no more volume, the reaction moves backward. Wherever there are more moles, the reaction will move. And I don't know why this happens, and I'm sure there's a very good reason. But backward, wherever there are more moles, and in that case, you will see more reactants than the products. But if you decrease the volume, so yeah, you're pushing the oxygen molecules and you've given the heat to form, collisions and, all those chemical kinetics, and that gives you the backward, this gives you forward. So the reaction is going to move forward. So in that case, we will see more ozone, right? And more products than the reactants. Okay. But if you add a catalyst, what happens? No change. Catalyst only increases the rate, but it does not shift the direction of the equilibrium. So this finishes the homework for this chapter. It's a small chapter, but very interesting chapter. And, but I highly recommend that you guys should also practice on your own. Many problems, I can only show you the thought process in doing the homework, but practice only comes through individual learning. Okay, guys, thank you so much for watching, and stop recording.